Hello, everyone! It is Saturday once again. And it's time to keep getting into formal logic. Or mathematical logic, as the case may be. So, we went over a brief overview of why some people might be interested in getting into mathematical logic. What does it mean in terms of it being a model for abstraction and mental discipline? How useful it is for understanding mathematical thinking, which is a very weird, highly abstract, very rational mode of thinking that some humans develop. And we saw some of the political benefits of that kind of clear yes or no kind of thinking. We also went over some of the limits or how it by itself is an inadequate mode of thinking. But we can all benefit from the idea of working out, exercising our thoughts in a model of thinking that has very clear methods for knowing whether we are right or wrong, correct or incorrect, whether something follows or it doesn't follow. We also went over a brief introduction about how we're going to treat this formal language. We're going to treat it as a model, as something we use to study a much more complex phenomenon. With the understanding that the model is not the real object. It does not capture the totality of the event with all its richness and detail. We are only studying some parts, which we call the essential parts, and discarding a lot, which we call the irrelevant parts. Now, whether something is relevant or irrelevant is not the case in an objective, absolute sense. Things are relevant or irrelevant to our model according to our goals and methodologies. So in this model, in this tiny, very limited language, formal fake language that we're using, we're gonna calculate propositions. A proposition is a very abstracted, also very limited mode of understanding a statement. In this logic, statements can only be composed of a single declarative sentence. So things like Walter Scott wrote a novel. Stuff like that. If I want to write Walter Scott did not write a novel, then I use some of the extra symbols that we went over last week as well. We will use a symbol that is negation. So we went over how we're going to model propositional statements. We're going to model them with a single capital letter. We have a non-infinite but arbitrarily large amount of letters. So if we ever feel like we're running out of letters, it's fine. We can just add another one. If we run out of the alphabet, then we start again with A1, A sub index 1. And if we run out of another alphabet, we start again with A sub index 2. So we can always produce one more letter. For most examples, unless we're a computer, we will only use at most 8 propositional letters. And by treating propositions as things that are only true or false, we can have a combinatory matrix of all possible states. And we call that combinatory matrix a truth table. So because A and B can only be true or false, the combinatory matrix is 2 to the n, where n is the amount of variables we're using or propositional letters we have. So if we have 2 letters, we have 2 to the n, 2, 2 to the 2, 2 times 2, 4. We have 4 combinations, possible combinations of truth values. A chunk where both statements are true, one is false, the other true, one is true, the other false, and both are false. So if we have 3 statements or 3 propositions, we will have 2 to the 3, which is 2 times 2 times 2, 2 times 2, 4, times 2, 8. 4 will be 16, 5 will be 32, 6 will be 64, and so on and so on. It literally grows exponentially, and that's why we rarely, if ever, study truth tables of more than 8 statements, and even that is quite troublesome to calculate. So we are studying Introduction to Mathematical Logic by Mendelssohn, and we stop here the exercises because it doesn't make for good streaming. But I did do the exercises as homework. Let me show you. New input. So I have a crap ton of windows open. Let me put it inside the frame. There we go. Yay! So this is LibreOffice. Like, honestly, at this point, I don't see why people should use any other Office suite, especially not Microsoft. LibreOffice is free, works perfectly fine, has basically all the tools from the Microsoft licensed product. This is the equivalent to Microsoft Excel, LibreOffice Calc, used for calculations. So, because this program uses cells, it is very comfortable or suiting. Okay, Hot Rod Mac Awesometon, thanks for joining us. But have you considered that this is free and doesn't have any so-called AI? I mean, maybe if you can find like an older version of Excel and obtain it by sailing the 7 seas, I will argue that's better. But free, comfortable, does mostly the same for 98% of users. Anyways, I was just explaining that what the heck this program is. So let me switch over from the Excel to the homework. Okay, so last session we designated the exclusive OR. A XOR B stands for A or B but not both, which is basically the truth table of the biconditional but negated. So yeah, pretty simple. So we're gonna start with 1.2. Construct truth tables for the statement forms either A implies B or not A. Okay, so let's go with that one. That is the one I have here on top. So first, I will assign the letters their canonical order. A comes first, so I will put either A is true or false, true, false. And then B is true, true, false, false. The canonical order is basically just a method to make sure that you're covering every possibility. It starts with the first proposition letter that appears, having 1, 1, 1, 1. and the next one will be 2, 2, 2, 2, and the third one will be 4, 4, and the third one will be 4, and the fourth one. Hey! Hey! Thanks for the sub! Okay, so sorry for the interrupt. Yeah, it goes by 1, 1, then 2, 2, then 4, 4, then 8, 8, then 16, 16, and so on, so on. Okay, Hotrap Osanton says, I bought Microsoft Office 2024 because of the Lambda helper functions. Map and scan really allow it to do stuff the other stuff just can't do. But I don't disagree that for 99.99% of people, LibreOffice is fine. I think it has feature parity with Office 2016. Yeah, pretty much. Lambda helper functions are pretty advanced. And I think that most people who do even know what Lambda helper functions are can code them for themselves if they need to. Anyways, so let's continue. So we have the canonical order true, false, true, false, true, false, false. And then here I put the numbers. Like, which do you feel first? 1 goes first, so 1 is just the letters. So it's just copy and pasting. A is true, false, B is true, false, false, and then A again. And then the second one to fill are negations. Because this negation applies directly to an atomic term, to a proposition, A. So negation switches. If something is true, then the negation is false. If something is false, the negation is true, and so on. So we have false, true, false, true. Then the third step is filling out this material conditional. The material conditional is only false when the first element is true and the second is false. So true implies true, yes. False implies true, yes. True implies false, no. False implies false, yes. Remember that another way of saying the conditional is less than. 1 is less or equal than 1? Yes. 0 is less or equal than 1? Yes. 1 is less or equal than 0? No. 0 is less or equal than 0? Yes. And then we have the disjunction, which is as long as one of the values is true, it is true. True or true? Yeah. True or false? Yeah. False and false. Wait. True or false? True. True or true? Yeah. False or false? No. True or true? Yep. So ultimately, adding or not a didn't change this at all. It didn't add any information adding the disjunction not a to this formula already. And this is a truth table for the first statement. The second statement is a lot longer. Let me check if I... Yeah, it is. If A implies that B implies C, then that implies that A implying B implies A implying C. That is, I think, the principle of extrapolation. I think it's called. Let me check. I mean, when I say the principle of extrapolation, it's the principle of extrapolation in formal logic. Anyways, yeah, that is correct. So let's go over the truth table. We have our three propositions. The first one is 1, 1, 1, 1, 1, 1, 2, 2, 2, 2, and the first one is 4, 4. See, that's the canonical order. So if you know how to count in binary, you can tell that this is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So another way, if you know how to count in binary, of knowing when you have the canonical order is that if you go from the bottom to the top, you're basically following or counting in binary. So this in binary is 0, this is 1, whoops, this is 2, 3, 4, 5, 6, and 7. And yeah, you can do a lot of clever math and automation, whatever, with this approach. Okay, so once again, I have here the numbers that tell me which part of the formula I fill first. And that's also why we use parentheses. The parentheses, much like in algebra, tell us which is the order of operations that want to take place. The statements nested inside the most parentheses are the ones that are the most primitive, or the ones closest to raw propositional statements, and therefore those are the ones that go first. So I fill out the letters for the propositional statements. Sorry, I fill out the truth values for the propositional letters. So A gets true, false, true, false, true, false, and so on. B gets true, true, false, false, and blah, 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 blah. And then I will fill out this column. B implies C. So again, the only space I have to worry about is true implying false, true implying false, everything else is true. If you know about Claude-Shannon information theory, that may ring a few bells. Basically, you only have to concern yourself with perceived differences. Since there are more true than false rows, you only need to memorize the false rows. Those are the ones that are exceptional. Those are the ones that add information to the otherwise monotonous truth. Okay, then 3. Again, I'm following the order of these parentheses. This is the function outside all parentheses, so this is going to be last. So I fill this one. I could have gone for this one or these two. It's fine. Again, the only space I have to worry about is true implying false, true implying false, everything else true. Another conditional, true implies false, false, true implies false, false. So then I have to compare if this column implies this column. So truth implies truth, yes. Truth implies truth, yes. Basically, same. The only space I have to worry about is truth implying falsehood. So the only ones I really have to worry about are this and this. Truth implies falsehood? No. Falsehood implies falsehood? Yes. So now I'm gonna fill this one. This is step number 6. And again, I only have to worry about false, false. True implies false? No. False implies false? Yes. So finally, the last connective I have to map out is if this column, if column 6 implies column 5. So I only look at the falsehood. This is the only relevant case in which this could fail. And now it turns out that falsehood implies falsehood. So that is true. And therefore, this column is all true. And that is a very funny result, because it means that no matter the case of whether A or B or C are true or false. Hello, Rupert! We're doing the homework. So this means that this formula, this big chorizo of a formula, regardless of whether B or C or A are true, it is always true. We call this in formal logic a tautology. And this means that this and any formula that can be described as this is always mathematically valid for this system. Very important. only relative to this system or systems that can be reduced to this, that function in this manner. There are other logics in which the conditional is interpreted differently, and so this may or may not be true. But in classical mathematics, it is basically an eternal truth. And you, maybe at this point you'll understand that when I say eternal truth, it is a lot less exciting than it sounds. But in classical mathematics, it is an eternal truth that if something implies that a second object implies a third object, then if the first implies the second, that means that the first one also implies the third. Basically, if B implies C, and this is implied by A, then if A implies B, that also means that A implies C. If this is true, then this is true. So if we were to take this as a sort of argument or theorem, we will have essentially proven that this is a mathematical theorem of sorts. That's what happens when you get all truths on a truth table. Let's check the homework again. Write the abbreviated truth tables for A implies B and A or not C if and only if B. Okay. A implies B and A. Pretty simple. Since these are the abbreviated forms, I'm really happy that you're seeing it, Hot Rob. Since these are the abbreviated forms, I don't have to bother with putting the A, B, and C. We'll just put it directly. So A, again, is always true, false. B is true, false. Not because A is A or B is B, but because A comes first, B comes second. So A implies B. We've done it several times already, so we only care about the third row, which is true implies false. And A is true, false. Okay, so conjunction. Only true if both parts are true. True and true, yes. True and false, no. False and true, no. True and false, no. So this formula is only true if both elements are true. Basically, let's look at what this formula is saying. If A is true, then B is true. That's what this part is saying. A implies B. And also, A is true. Think about the most basic of syllogisms, or think about the most basics of a conditional statement. If I jump from the Eiffel Tower, I will fall. If A, then B. A implies B. Me jumping from the Eiffel Tower implies I fall. But also, you know this for a fact, I jump from the Eiffel Tower. That is A. If A implies B and A is true, what does that tell me about B? Rupert? Any ideas? B has to be true. Exactly. And we have proven this through this truth table. The only possible scenario in which this formula is true is if both are true. So if this is the case, then B has to be true. Okay, the last truth table from the homework. A or not C if and only if B. This is just a pure exercise. There's nothing particularly interesting about this formula. A gets true, false, true, false, true, false. B gets true, true, false, false, and so on. We follow the canonical order. Okay, Rupert. Also remember that everything from this series is gonna be archived on YouTube, so don't worry if you miss it. So we have C, and then we have to negate C, so we invert it. Instead of true, false, 4 times, we have false, 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 true, true. And then A or not C. Because in these four rows, this is true, this is automatically true, I don't have to worry too much. True or false, true, because at least one is true. False or false, okay, both are false, it's false. True or false, true. False or false, false. So we have this, if and only if, B. And if and only if, remember, only shows true if both values are the same. So true is the same as true, yes. False is the same as true, no. True is the same as false, no. False is the same as false, yes. True is the same as true, yes. True is the same as true, yes. True is the same as false, no. And again. Nothing too particularly interesting about this example, just that it has 4 more rows, I guess. And it's a slightly tricky formula. Okay, let's go to the other part of the homework, which is formalization. Okay, I hope that is legible. Let's check the homework. Okay, we are now on 1.4. Write the following sentences as statement forms, using statement letters to stand for the atomic sentences. That is, those sentences that are not built up out of other sentences. This is something called formalization, basically taking sentences from ordinary language and presenting them in the highly abstract language of formal logic. I think they are a funny and interesting exercise, but I ultimately do not think this is my personal philosophical stance. This is not a fact. This is just I'm just being clear and honest for the sake of disclosure. I do not think that it serves of much use. Ordinary language is far more rich, contextual, and varied than you can meaningfully capture using proposition logic. However, that is ordinary language. If you hang out with a bunch of mathematicians, or if you're trying to understand how to play Magic the Gathering, then I think formalization is a huge help. Because those are very mechanical, very abstract modes of language. And we want to have like very strict, narrow definitions on how to use those words. Okay, disclosure over. So we're gonna take some of these sentences and we're gonna pretend they are like mathematical sentences and simplify and formalize them. Also, content warning, the author will eventually do a small racism, I think. I'll let you know. Okay, so the first sentence is, I think it will also be helpful in choosing the LSAT. Yes, because the language used in exams and similar places has to be quantified, has to be reduced to something a computer can understand. So yes, that is another context in which this violence we're going to do against language is acceptable. Okay, if Mr. Jones is happy, Mrs. Jones is not happy. And if Mr. Jones is not happy, Mrs. Jones is not happy. So the first atomic sentence is P. I personally prefer P and Q and R and S above A and B. Just personal preferences. That nothing too important. So my first atomic sentence is Mr. Jones is happy. And my second atomic sentence is Mrs. Jones is happy. What am I doing? Why did I put the negation there? Negations are complex. We have a symbol for negation. I don't need to put negation on my atomic sentence. So the only two statements that I'm concerned with, the only two propositions is Mr. Jones is happy and Mrs. Jones is happy. This, by the way, is not very helpful design for dyslexic students. So don't do this kind of exercise if you want to be dyslexic friendly. Because it is very easy to just forget or skip out the Mr. and Mrs. If you or your students have like some sort of reading issue going on. Okay, so the first part of this statement is if Mr. Jones is happy, then Mrs. Jones is not happy. If Mr. Jones is happy, then Mrs. Jones is not happy. Here's the negation. And we're gonna mostly model and as conjunction because the and in ordinary language tends to, notice, tends to, and I'm not saying it always or automatically or that it means the same. It tends to be adequately modeled by the conjunction. But the conjunction and the word and in ordinary language are different things. Okay, but in this case, the most fitting function connective that I have for this and is the conjunction. Because this sentence is telling me that both of these things are true. So if Mr. Jones is happy, then Mrs. Jones is not happy. And if Mr. Jones is not happy, then Mrs. Jones is not happy. So, because in this logic, everything is either true or false, that's all the combinations we have accessible. Either Mr. Jones is happy or he's not. If he is, Mrs. Jones is unhappy. If he isn't, then Mrs. Jones is unhappy anyways. So from this, we can conclude that Mrs. Jones is not happy, ever. Second sentence. Either Sam will come to the party and Max will not, or Sam will not come to the party and Max will enjoy himself. Now, this is tricky because here I have a fragmented sentence. Max will not, by itself, is not a full sentence. I have to interpret what this means. I have to use my non-formal, non-logical part of the brain to see, oh, what is the context? What is the semantic awareness of this conversation that I can understand that will allow me to replace this fragment of a sentence with a full sentence? Well, we're talking about coming to the party. So my first atomic statement will be Sam will come to the party. And once again, I did the same error. I added an unnecessary negation. It is Max will come to the party. Max will not tells me that we're talking about Max coming or not coming to the party. Notice that this is something I cannot rely on pure mathematics or pure logic to tell me about. I have to understand the meaning of language and context and generally what this means, what does coming to a party means in order to fully formalize this. This is not a proof that computers cannot understand semantic language, but this is a valuable intuition. It's a useful notion to help people understand how difficult it is to reason through implied context. It is something that mathematical logic cannot do. So P is Sam will come to the party, Q is Max will come to the party, and then we have Max will enjoy himself. Logically, formally speaking, I have no explicit connection between going to a party and enjoying myself. I have to treat this as separate statements. So my third atomic statement will be Max will enjoy himself. So either is commonly modeled with a disjunction. So one of two things may happen, maybe both. Either Sam will come to the party and Max will not. So P is Sam coming to the party, Q is Max will come to the party, and because this is will not, so we negate it. So either this happens, either Sam party or Max will not party. This is the end. Or Sam will come to the party and Max will enjoy himself. Hey, Max will enjoy himself at the party? Who knows? I have no explicit rules that tell me when, where, how, or why Max will enjoy himself. I have no sense of causation, relevance, or context in my formal system. All I know is that either one of these things may, or maybe both will happen. It turns out that both cannot happen at the same time, because one implies Sam and the other implies not Sam. But for example, if I am in this situation, I know nothing whether Max will go to the party or not. This logic does not rescue causality at all. All I have... This is what it feels trying to piece together inferential meaning in a conversation between neurotypicals. Yes. Because we autistics tend to be very focused on explicit information, we have something like an inherent bonus to logic. I mean, not all autistics, but myself and many of my colleagues are autistics. And for some reason, this highly explicit method of information retrieval is appealing to us. Okay. Here is a good example of why I suggest studying logic with a group or a teacher, because Mendelssohn is an asshole for doing this. The third sentence is, a sufficient condition for x to be odd is that x is prime. This sentence, depending on your needs, is not really well modeled. What about 2? What do you mean, what about 2? Hot drop. Oh, I don't know if this sentence is true. But notice that it is only saying a sufficient condition. A sufficient condition? No, you're confusing sufficient and necessary. A sufficient condition means that the condition is enough to satisfy or to prove or to imply the element being conditioned. This statement is not saying that in order for a number to be odd, then it has to be a prime. It is saying the other way around. It is enough for a number to be prime to know that it is odd. But Hot Drop is right. However, I do not care about the truth of this statement. I am only tasked to model it. Furthermore, propositional logic is so primitive that I cannot understand variables. we do not have variables in propositional logic. So I cannot correctly understand or model what is X in this sentence. In this sentence, if I use my human brain and my context awareness, I know that X is a variable. But my powers of description within propositional logic do not allow me to understand what a variable is. In this system, X is a proper name. I do not know what X means. I do not know what an odd number means. All I know is that there is a logical relationship between two statements. X is an odd number. What does X mean? I don't know. X could be the name, it could be Malcolm X. It could be a variable. I don't know what a variable is. I have no way of modeling variables in this system. And Q is a prime number. Like, how do we know that we're talking about a number and not just an object named X? How do we know that this X is the same X? We don't know. Our logical system is so poor, is so limited, that we cannot answer those questions in a meaningful way. All I know is that a statement is sufficient for another statement. That's it. A sufficient condition for X to be odd, so X is a number. I mean, hell, I don't even know if X is a number. I mean, I can tell by interpreting this as a mathematical statement, but honestly speaking, this sentence by itself does not tell me that X is a number. Like, if I wanted to be like super precise and methodical, I will just say this. X is odd. X is prime. What does odd and prime mean? I don't know. I mean, I as a human being, yes, I do know. But me as a formalizing machine, I do not know and I do not care. All I care about is the logical relation, the material implication between these two statements. And sufficient means that it is sufficient for a statement that another statement. So Q, X is prime, is sufficient to imply or to satisfy P, which is X is odd. Does this statement tell me anything about mathematics, what a prime number is, or... Yep. This kind of kept throwing me off in the LSAT practice test, real world knowledge being like, well, one of your axioms is wrong. Yep. This kind of shit is really useful if you want to train people to not ask questions and just follow instructions exactly and explicitly as stated. Which can be pretty perverse. But ultimately, this kind of thinking is the thinking that gave us computers. So computers should do that. Should not ask questions, they cannot ask questions, they cannot infer meaning. They will just follow the instructions explicitly. Okay, we have another curveball. A necessary condition for a sequence S to converge is that S be bounded. I don't know what a sequence convergence is. I don't know what a sequence bounding is. All I care about, for the sake of this exercise, for the sake of this homework, is the material relationship between two statements. A sequence S converges and a sequence S is bounded. Necessary means that it is guaranteed by another. Means that if I am necessary to something else, that means that if something else appears, I am a necessary component of it. So I am implied by the other statement. So being bounded is a necessary condition for converging. And so converging implies bounded. That's it. That's all I can model in the system. A necessary and sufficient condition. Okay, here's the one that is I don't know, arguably racist or kind of orientalist. So yeah, refer your criticisms to Mendelssohn. I am just doing the homework. I will refuse from interpreting this too closely. A necessary and sufficient condition for the sheik to be happy is that he has wine, women, and song. And of course, we're going to be talking about the Iron Sheik to avoid any important implications. So we can model this in two ways. I went for the extra one, because why not? The sheik is happy, the sheik has wine, the sheik has women, the sheik has song. I could have just piled all three of them in one statement, but again, I wanted to be extra. Necessary and sufficient means that the implication goes both ways, and that is a big conditional, or a material equivalence. The sheik is happy if and only if the sheik has wine, sheik has women, and the sheik has song. Okay, so necessary and sufficient condition means that they both go hand in hand. One implies the other, and the other implies the first. Fiorello goes to the movies only if a comedy is playing. So this one is tricky. You have to think about what you know depending on the case. This is the tricky part. Only if. Hopper McAwesometon asks, does Q parentheses R and S need to be like that, or could you put it Q and R and S? When you're a beginner, I strongly suggest that you use parentheses correctly. Later on, we can prove that the conjunction and the disjunction are both associative and commutative. So as long as you have pure conjunctions and pure disjunctions, you can more or less ignore the parentheses. But for the sake of proper education and for being rigorous, I would suggest starting with parentheses. But later on, you won't need it. And most mathematicians won't use them, won't use the full parentheses. They know that the conjunction is both associative and commutative. What does associative and commutative means? What did I do? Okay, so associative is any mathematical function in which the order can be swapped. No, wait, no, this is commutative. This is commutation. So if this function, whatever the asterisk function means, is commutative, then that means that A function B is the same as B function A. The order doesn't matter. Oh, thank you, Hot Drop. Associative means that you can associate or switch between it's this side that association means that the hierarchy of functions does not affect the result. A more natural example of a function that is both associative and commutative is a sum. Let's prove it. Well, I mean, we're not gonna fully prove it, because mathematically proving this requires it is way more trickier than it looks. But let's provide an intuitive example that may help to illustrate the point. 1 plus 2 is the same as 2 plus 1. That is commutation at work. And 2 and 1 plus 2 plus 3 is the same as 1 plus 2 plus 3. So basically, when a function is both associative and commutative, it means that the order doesn't matter. I wish someone had explained this to me when I was doing algebra. Like, if I had just been explained shit like this in middle school, I would not have hated math during high school. I see where you're coming from, actually. I generally overuse brackets in my Excel functions because I find them, it makes, yeah, that's pretty much the same, yeah. Yeah, if someone had explained me while I was learning algebra that I can do this whole swapping and playing with the symbols and bullshit because they have these properties of association and commutation, things would have just been bitchy. Okay, so this is association, and this is commutation, and this is association. Okay, and because the conjunction is commutative and associative, I asked questions like this and all I got was, it's important and you learn why later, stop interrupting. Yep. Same. So because the conjunction and the disjunction are commutative and associative, you can later on ignore some of the parentheses or brackets or whatever, but for now we'll use them. Okay, so back to Fiorello. Fiorello goes to the movies only if a comedy is playing. So the best way to puzzle what the hell an only if means is what guarantees what. If a comedy is playing in the movies, does that guarantee that Fiorello is watching the movie? No, it does not. The fact that there is a comedy does not guarantee that Fiorello is watching it. Exactly. yeah, Hot Rod got it. But if Fiorello is watching a movie, what do you know about that movie? It's fine, Rupert. Everyone trips up with this kind of shit. It's gonna have Will Ferrell's. I mean, not necessarily Hot Rod. Yeah, it's gonna be a comedy. We don't know who Will Ferrell is. Will Ferrell does not appear in this sentence, so for the sake of the system, we have no idea what comedy means, who Will Ferrell is, and so on and so on. So yes, Fiorello watching a movie or going to the movies is what guarantees that the movies are showing a comedy. So P implies Q. Fiorello going to the movies implies that the movies are playing a comedy. Comedy does not imply Fiorello watching. But consider the following. Maybe this will be more clear. If there are no comedies watching, what do we know about Fiorello? Fiorello only goes to the movies if a comedy is playing, but we know that there are no comedies currently playing. What do we know about Fiorello? If no comedies, then yep, exactly, Rupert. He ain't going to the movies. Exactly, Hot Rob. This sentence and this sentence, or rather this formula and this formula, are exactly the same. They mean the same thing. But maybe one presentation is more clear. The fact that you can convert this from this, it's called transposition. And it sounds like logicians doing a magic trick. But yeah, it's a pretty handy phenomenon. If you don't understand something, ask yourself, what do I know if one of the elements happen? What do I know if one of the elements does not happen? And then play around. This little trick has helped my reading comprehension immensely. The bribe will be paid if and only if the goods are delivered. That's pretty simple. If and only if means both ways. So the bribe will be paid if the goods are delivered. If Fiorello went to every comedy, then it will be P if and only if Q. Yes! You are absolutely correct, Hokrop. Gold star. If x is positive, then x to the 2 is positive. We don't know what x means, we don't know what x2 means. For all intents and purposes, in our logic, they are proper names. So, if the first one, then the second one. P implies Q. That's it. Karpov will win the chess tournament unless Kasparov wins today. I don't know if these references click today. Anatoly Karpov and Garry Kasparov were Soviet chess masters until Garry Kasparov betrayed the Soviet Union and became a liberal. And he basically just posts George Bush style propaganda on Twitter these days. I don't have a positive opinion of Kasparov, I'm sorry. Meanwhile, Karpov was part of one of my favorite memes of all time. It's so good I have to show... No, wait, no, I can't show it because it's gonna go on YouTube. But it's really so good. Karpov final... I'm gonna link it on chat so you can all watch it for your enjoyment. It's one of the greatest memes of all time. Anyways, that aside, let's just ignore who Anatoly Karpov and Garry Kasparov are. Karpov will win the chess tournament unless Kasparov wins today. Is it the one with the baby? Toddler, but yes. I'll be honest, I thought Kasparov died in the 90s. No, only his conscience. God, I need to stop doing that. Yeah, it is. So yeah, it is that Anatoly Karpov. So, important chess guy. Okay, anyways, that's just a reference. For the sake of the exercise, we don't care who Karpov and Kasparov are. So, Karpov will win the chess tournament unless Kasparov wins today. Again, here I interpreted wins today as wins the chess tournament. If I wanted to be like a full computer, I would have written this. Because winning today does not mean the same as winning the chess tournament. You can win today in multiple ways. So, always a deliberate human choice when we are formalizing and interpreting. So I choose to interpret it this way, and I'll explain why later. Okay, so either Karpov wins unless Kasparov wins. It's tricky. Strictly speaking, we know the following. P is Karpov wins. Or Kasparov wins and Karpov doesn't. So I am interpreting this sentence as a possible two forking roads kind of situation. Karpov wins or Kasparov wins and Karpov doesn't. Either Karpov wins or Kasparov wins and Karpov doesn't. And here's the truth table. Or if Karpov doesn't win, that implies that Kasparov won. This formula are equivalent to P or Q. Basically, either one of them will win. Now, I have a choice. because this sentence can be true if both players win. Because in formal logic, Karpov will win the chess tournament unless something else happens, will automatically be true if this part is true. But what if I want to add more human sense to this sentence? It's like, okay, hold on. But in a chess tournament, and you are modeling this as a chess tournament, there is only one winner, so it is not possible that both win. Okay, if you're interpreting in that way, then we do this, which we showed earlier that this is basically XOR, exclusive OR. But the problem is, where from this sentence does it say explicitly that chess tournaments only have one winner? That is something only I can extract if I use my human senses and my human language and use the information about the social element that is a chess tournament and what chess means. Karpov could be tied in points with an unnamed third party, and then if Karpov doesn't win the game with Kasparov, then Magnus Carlsen wins the tournament by default. So Kasparov and Karpov both lose the tournament, even though Kasparov won the game today. That's funny. I hope you mean it's a joke, because while that is plausible using our human senses and our human logic and our context awareness, we are not functioning as humans right now. We're functioning as formalizing machines. And a formalizing machine can only use the information given by the input. And in this input, there is no mention of Magnus Carlsen or what being tied in points or what a third party is. None of those words appear in this sentence. And so we do not understand what any of that is as formalizing machines. So, did I get through what the fundamental problem of formalizing is? And from that you can extract a lot of philosophy, very interesting philosophy of language about how we talk and how we communicate and how we are different from computers. Anyways, that was the homework. I want to do an exercise with chat. Hodrobak Awesometon says, I'll be honest, when I read it, I didn't see Kasparov as having a chance to win the tournament, only the game, and in doing so denying Karpov the tournament win. Yeah, again, because the exercise only said wins today. What does wins today mean? I don't know. Wins today could mean so many things. But formal logic, propositional logic, only cares about this part. Unless the content of these statements is unreadable and unscrutable for formal propositional logic. It is reduced to P and Q and maybe logical connectives. So what I understand from this is that P or Q and not P. That is how I choose to interpret the unless. Anything else, how chess tournaments work, how points work, whether ELO is involved, that is my human brain trying to feel the meaning. That is using information I have from the meaning of words, from my social awareness of what a chess tournament is, from what chess is. And unless explicitly programmed with those instructions, I do not have access to that information when I formalize. Would it have been wrong if I put Q, Kasparov wins today instead of Kasparov wins the tournament? No, not at all. It is ambiguous. Whether we choose to interpret wins today as in wins the chess tournament or not, that is something that propositional logic cannot tell us. That is teleological thinking, thinking for a purpose. And computers, so far, cannot do that. And when we think through propositional logic, we're basically functioning as computers. The ambiguity is valid. I, as a teacher, cannot tell you which of these following formalizations are correct or incorrect. Well, I mean, all of this I will rate as valid. And that is a very good reason why I think another good reason why logic manuals shall be studied as a group and with the help of an expert. Oh, and this needs another parenthesis. There we go. Okay. Now let's do something fun. Insert page break. Let's use these tools to do some knights and knaves puzzles. Knights and knaves puzzles You thought that was fun? Okay. I'm glad you did. Yeah, Rupert. I am a follower of Vygotskian pedagogy. I think that learning is best in a social setting. I have seen it happen in real time with other streamers. Study groups, educational streams where people participate, they tend to be much more effective at getting people to learn and getting people interested than singular study. So that's why I'm picking up the streaming thing, because I think it is more effective and more in line with my pedagogy than just making videos. Okay, so Knights and Knaves puzzles. And this comes from a book by Raymond Smolin, which is a great guy, called What is the Name of the Book? Like, what is the name of the book? Of this book is the name of the book. We logicians have an obsession with self-reference. So the rules are as following. In the island of knights and knaves, there are only knights or knaves. Knights, okay, let me write explicitly the rule. In the island of knights and knaves, there are only knights or knaves. You can't be a knight and a knave. It's either or. Knights always tell the truth. Knaves always lie. Okay? Those are the rules for the Knights and Knaves puzzles. If you play Dungeons and Dragons or similar tabletop games and your DM puts the whole hold, traveler! There are two guardians in front of your path. One always tells the truth and one always lies. That is a Knights and Knaves puzzles. Okay, so Hot Drop McCustomton says, I need to take things apart and put them back together to really understand a concept. I can do that by myself with some things, but for something like this, it really helps so much to be able to have someone that questions of, yes. Yeah, that will get us to something called the zone of proximal development. One guard always lies and the other guard is always wrong. See, being wrong is not the same as lying. Anyways, so with these rules in place, let's tackle this puzzle. There are only two people, A and B. Oh wow, look! Capital letters, almost like they propositions. Each of whom is either a knight or a knave. A makes the following statement. At least one of us is a knave. What are A and B? So the problem is that in propositional logic, we do not have the at least one part of our language. But we can do the following. We can make a truth table. because there are two people and they have two values, we have the same function as truth tables, 2 to the n, and we have either knights or knaves, so it is, and we have two people, so it's 2 to the n, 2 times 2, 4. So we have the following things. So either they are both knights, one is knight and the other is a knave, one is a knave and the other is a knight, and both are knaves. See, we're basically doing a truth table, but with knights and knaves. So A makes the following statement: at least one of us is a knave. So we can simply go through every possible combination. If both are knights, and this person says A, and we're assuming she's a knight, at least one of us is a knave. Is this statement true? Is one of them a knave? We're assuming that both are knights. So because A is a knight and she has to tell the truth, and both are knights, therefore the statement, one of us is a knave, will be false. That will be a knight saying a false thing, which is impossible, which means that this line cannot be the case. They cannot be both knights. Okay, let's imagine they are both knaves. If they are both knaves, then A is a knave, and she says, at least one of us is a knave, which will be a true statement. That will be a knave telling the truth. Therefore, this position is impossible. Okay, let's go through this situation. A is a knave, and B is a knight. A knave saying at least one of us is a knave, while she herself is a knave, will be telling the truth, and therefore she will be a knight, not a knave. Contradiction. This position is impossible. So now we only have one possible state of things. A is a knight, B is a knave, and A says, at least one of us is a knave. Yes, that is true. B is a knave. Therefore, this position is valid. It is the only one remaining, and thus we have to be in this position. A has to be a knight, and B has to be the knave. And notice that I'm not saying, I'm saying it with particular strength. Has to be. It is necessary. It is the only possible combination that is allowed within this set of rules. That is deduction. That is the kind of thinking that is behind a mathematical proof or theorem. That is mathematical thinking in action. I have a methodology. I have exhausted all possible states, leaving me with one and only one possible conclusion. It has to be this. There is no other possibility. At least if everything in this model universe remains constant and consistent. Okay, let's try another one. Another knights and knaves puzzle. Same rules. Now I would like if chat helped me with this one. I'm gonna copy, because we also have A and B, I'm just gonna copy the table, and I'm gonna erase the formatting. Either I am a knave or B is a knight. So how will we formalize this as a formula in propositional logic? Either tends to be modeled by the disjunction. Either I is a knave. I'm going to formalize with knave A. No, nen A. Or B is a knight. we can do another thing. Because knaves are the opposite of knights, we can say that instead of getting a new symbol for knaves, we can just say not knight. Hot Drop says, I wonder what knaves add to their society, or do they just have really good business lobbies to fund the navel-gazing party so they can enact pro-knave gerrymandering? Turns out that communication will be impossible if everyone only said the truth, Hot Drop. Because you will have a monotonic society. You will only have one value, which is true, and without anything to contrast truth against, you wouldn't have information. Food for thought. Anyways, so either not knight or be knight. This sentence is true whenever B is a knight. So 1 and 3. And this sentence is true whenever A is a knave. So 3 and 4. So the only place this sentence is false is in 2. Okay, let's go case by case. Either I am a knave or B is a knight. What are A and B? If A is a knight and he says this, is the sentence true or false? It has to be true. Because this disjunction is true as long as B is a knight. And therefore this is consistent. It is consistent with both of them being knights. Okay? Either I am a knave or B is a knight. If we're assuming that A is telling the truth, she will be a knight. So let's see. B is a knight and this situation is false. A being a knave in this situation is false. Therefore, she will be saying something false. But she will be a knight, which means this situation is impossible. Either I am a knave or B is a knight. In this case, in which she's a knave, she has to be lying. This statement has to be false. But if she's saying or B is a knight, it will be true, because B is a knight. Therefore, this situation is impossible. Either I am a knave, and she's a knave, or he or she, whatever. I keep calling A's she because in my head A's are Alice and Bob. Sorry. This will be a knave calling themselves a knave, and it will be true. So this statement will be true, said by a knave, and this situation is impossible. Therefore, they are both knights. So, what do y'all think? One more knights and knight puzzles? Okay, actually, we cannot do the other one because we need to understand what contradictions and tautologies are. So we will have to progress with Mendelssohn. I'm so sorry, no more puzzles for today. But you can buy the book. I think hopefully it's cheap, or you can just get it. It's literally What is the Name of This Book by Raymond Smullyan. There are also like automatic knights and knaves puzzles. Yeah, there's plenty of free games and automated generators for nice puzzles online, so feel free to plunder them. As you see, just mapping out all possible combinations and going over them one by one is a perfectly valid method to tackle many basic knights and knaves puzzles. Anyways, let's start going through some of the more same Rupert. Let's start going over some of the more interesting semantic concepts of processing logic. When mathematical logic talks about semantics, we're not talking about real linguistics, okay? We're just using that word to mean the part of the formal system that cares about the meaning or the values of the symbols. That's it. It's not real semantics. Okay, so remember from the homework, the A implies B implies C implies A implies B implies A implies C. A little bit of a tongue twister. Truth table where it turns out that all of them were true. Okay, think about that while I read. A third function of n arguments, and here an argument is the amount of propositional letters, and n is just the amount, is defined to be a function of n arguments, the arguments and values of which are the truth values, true or false. As we have seen, any statement form containing n distinct statement letters determines a corresponding truth function of n arguments. What this means in plain English is that a formula is or ends as a truth function, and n arguments is the inputs understood as propositional letters inside that formula. And here is some semi-complex math. It just means that it is what I meant by using the canonical order. Then the number of appearance of the propositional letter is what matters. And this is like the full mapping out of a formula in terms of a mathematical function. What is a mathematical function? I'll explain very briefly. It is an incredibly wonderful concept. So you have two sets. The domain and the codomain or image, also called image. And then the first set has any amounts of elements. We don't care. And the codomain or image has any amounts of elements. We don't care. And a function is a very specific type of relationship between these two sets that says the following. All of the elements from the domain have one corresponding element in the codomain. So this one goes to this one, 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 and so on. Okay? Each of these elements of this set has one corresponding element in the codomain or image. But we can have lingering elements in the codomain. We don't need to saturate the codomain. We only need to saturate the domain. Another thing we cannot do is one element of the domain having two corresponding elements. Okay, the domain has to be loyal and faithful. No relationship, bigamy or polygamy here. From the domain. Where's the selection? Give me a selection. Okay. But one element of the codomain can receive multiple elements of the domain. So this is allowed. Okay? So a function is a relationship between two sets such that the codomain is fully mapped onto the codomain. Every element of the domain has one corresponding element of the codomain, even though the codomain may have. So if the domain is mammals, a codomain could be vertebrates. It's more abstract than that. It's just a pairing. What does the pairing mean? Nothing. It's just this for that. A more intuitive example will be in teams. So imagine that the domain is the amount of players on the field. They're playing some sports ball. And you want to map out the players to their teams. Well, there are only two teams. So player A is from team red. Player B is from team blue. Player C is from team red. Player D is from team blue. Player A, B, C, D, E is from team red, and so on. No player belongs to more than one team, and every player belongs in one team. That is a function, even though teams may be composed of multiple players. Okay, so a truth function is a function that takes elements from our formulas. The domain here is a set of our formulas, and the codomain or image is either true or false. That is what makes something a truth function. It maps formulas onto truth values, true or false, in our classical two-valued logic. You can have, there we go. So in a truth function, classical truth function, there is only true or false. So we map out elements from our domain, formulas, into either true or false. We, in our classical logic, we cannot have the same proposition or same element or the same formula, whatever, have more than one value. You're either true or false. Something being true and false at once, we do not like. We don't like in classical mathematics. I have seen descriptions of functions as machines that transform the domain input into range products and whatnot, but it's more intuitive. This is more intuitive if you are autistic and you like really explicit methods, because it's more abstract. Most people do not like this level of abstraction. No, truth functions are not machines. They are just mathematical relationships. Anyways, in classical logic, our elements from the domain have to be assigned a value. They are either true or false. They cannot be true and false at the same time, and they cannot be unvalued. So yeah, that is a truth function. And we just have like a truth table is basically a map of all possible truth functions of n arguments. That is really what it's saying here, using a lot of slightly more complicated terms. No. Okay, whatever. Let's just leave it there. It's gonna erase when I close the document. Okay. So, a statement form that is always true, no matter what the truth values of its statement letters may be, is called a tautology. A statement form is a tautology if and only if its corresponding truth function takes only the value t, big T as in big truth, or equivalently, if in its truth value, the column under the statement form contains only t's, only truths. An example is a tautology A or not A, to be or not to be. The so-called law of excluded middle. Calling these kind of phenomenons laws It's basically an Aristotelian vestige. Most people do not believe that the law of excluded middle is a metaphysical law of the universe. Not anymore, really. But if you're working in a binary system, then yeah, it's basically an eternal truth because you made it so. I gotta start winding down for bed. I'll definitely catch up on the VOD later, though. Thank you so much for the lessons, and it's wonderful. I'm really glad you've been enjoying it, Hot Drop. Hope you have an excellent night. We're almost done, don't worry. I'll see you on the VOD. Okay. Other simple examples of tautologies are not A and not A, because A and not A is a contradiction. So the opposite of a contradiction is a tautology. The opposite of something that is always false is something that is always true. A if and only if not A. So it is false that not A is equivalent to just saying A. A and B implies A, of course. If two things are true, then they are true by separate in formal logic. And A implies A or B, because if something is true, then true or anything else, yeah. Beta, don't worry, Hot Drop, don't worry. It's fine. Beta here, beta is not part of our language, or Gothic B, whatever. I usually call it beta. Gothic beta or Gothic B or beta is not part of our language. It's just a variable of any formula in our propositional logic. It's said to logically imply. Is that a C or an epsilon? I have no idea. A formula is said to logically imply any other formula, or synonymously, a formula is a logical consequence of beta if and only if every truth assignment to the statement letters of B and C that makes B true also makes C true. For example, A and B logically implies A logically implies A or B, and A implies B logically implies B, which we saw earlier when we were going over the homework. B and C are said to be logically equivalent if and only if B and C receive the same truth value under every assignment of truth values to the statement letters of B and C. For example, A and not A are logically equivalent, as are A and B and B and A. We proved this earlier when we went over commutation. Okay, so B logically implies C if and only if B material implication C is a tautology. B and C are logically equivalent if and only if B, if and only if, or B conditional C is a tautology. Let me provide some examples. I don't like this garish red anymore. Let's paint it black. So we have A and not A. So A is either true or false. A is either true or false. We negate that. What do we get? False and true. We negate that again. Basically, we did a switch and then we ceased to switch. So we end up where we began. True and false. True is the same as true? Yes. False is the same as false? Yes. Therefore, A, if and only if, not A, is always true. It's a tautology. That by itself is proof that anything in this schema, like we can replace A for any formula, because notice that we're talking about not a particular statement A. We're talking about anything that has this form, anything that has this schema. A is the same as not A. Any formula negated twice is equivalent to the original formula. And this is a very brief example of what a mathematical proof is like. Assume B, which is B is, remember, any formula, any well-formed formula for language, logically implies C, which is any other. Hence, every true assignment that makes B true also makes C true. Thus, no true assignments that makes B true and C false. Therefore, no true assignment makes B implies C false. Because remember, B implies C only is false when B is true and C is false. Because that case is not possible, because we are saying that by the definition of what logical implication means, the material conditional reflects the process of logical implication in propositional logic. In other words, B implies C is a tautology. Now the other way around. Assume that B implies C is a tautology. Why the other way around? Because we're proving an if and only if statement. And an if and only if statement is only proven if we prove that this part implies this and this part implies this. So if we want to prove an if and only if, we need to prove both sides. A implies B and B implies C. And B implies A. I'm sorry. A implies B and B implies A. Do you see how formal logic is an exercise in this kind of somewhat perverse circular reasoning? Because we need the properties of logic to prove the properties of logic. And that is why us logicians are obsessed with self-predication, circularity, and self-reference. Anyways, so we're gonna prove the other way around. Assume B implies C is a tautology. Then for every true assignment, B implies C is true, and therefore it is not the case that B is true and C is false. Hence, every true assignment that makes B true makes C true, and that is the definition of logically implying. So B logically implies C. As you can see, this is a baby proof, but it still needs to be done. It has to be explicitly laid out. And the other one is basically the same thing, just even easier, because we have already defined the biconditional to be only true when both parts are true. And that is, well, that is equivalence. By means of a truth table, we have an effective procedure for determining whether a statement form is a tautology. Hence, by proposition 1.1, we have an effective procedures for determining whether a given statement form logically implies any other given statement form and whether two given statements are logically equivalent. Okay, so what is this funny term, effective procedure? That basically means computable. I just heard 1,000 computer scientists scream, I know, they are not exactly the same thing, but for all practical intents and purposes, they mean the same thing in our day and age. Whether an effective procedure means computable and vice versa is the Turing thesis, which is not something we can prove. But we basically go for it every time we turn on a computer, so it's fine. To see whether a statement form is a tautology, there is another method that is often shorter than the construction of a truth table. Is this particularly useful? Well, this is just doing the inverse. So instead of doing a truth table, we can do something that is called reduction to absurdity. We prove something true by showing that the alternative is impossible. So if we want to prove that something is a tautology, we can instead assume, okay, let's assume it is not a tautology, and if this is impossible, then I have proven it's a tautology. But that is okay. Let's do one, and this one I'm gonna end stream because it's not particularly good streaming entertainment. So what this person does is, okay, let's prove that A, if and only if, not B or C, implies not A implies B is a tautology. And to do that, I'm gonna do a reduction to absurdity. Reductio ad absurdum. I am going to assume that the main connective, this conditional, is false. In order for this conditional to be false, I need the first part to be true and the second part to be false. The sufficient condition needs to be true and the necessary condition needs to be false. The antecedent needs to be false. So the antecedent is what goes before the conditional. The consequent is what goes after the conditional. So I need to assume that the antecedent is true and the consequent is false. In order for the antecedent to be false, these two need to have opposite values. Okay, but in order for the consequent to be false, I need to have the antecedent true and the consequent false. So not A needs to be true, which means A needs to be false. And if A has to be false, then in order for this to be true, this has to be true as well. So not B or C has to be false. Sorry, it has to be false because I want A to be false and the B conditional to be true. They need to have the same value. And if A is false, then not B or C has to be false. And the only way for a disjunction to be false is if both elements are false. So C needs to be false and not B needs to be false, which means that B needs to be true, but I need B to be true here, false to be here, and true to be here. B cannot as truth function be mapped simultaneously to true and false. That is a contradiction. And if we model tautologies as big T, we're going to model contradictions as upside down T. Because a tautology is the opposite of a contradiction and vice versa. So this is a contradiction that is impossible, and because the truth function cannot assign B simultaneously both true and false, it cannot be the case that this sentence or this formula is false, therefore it always has to be true. Therefore, A, if and only if, not B or C, that implies that not A implies B, is a tautology. It is always true. It is an always valid schema for propositions in propositional logic. Not proposition, sorry. It is an always valid schema for formula in propositional logic. Okay, I am going to... Okay, okay, never mind. This is just another example. Fuck it, let's do it. In order for... Okay, we're gonna do this again by doing the opposite. In order for a disjunction to be false, both sides need to be false. So if this is false, then both sides are false. If a implication is false, then the antecedent has to be true and the consequence needs to be false. If this is false, then the antecedent needs to be true and the consequence needs to be false. In order for the disjunction to be false, both sides need to be false. Because I am assigning every letter a truth value and I have no contradictions, if A is true, B is false, C is false, that is enough to make this disjunction false it is consistent, and therefore there is at least one possible state in which this sentence can be false. Therefore, it is not a tautology. Funny, huh? How this kind of looks like a tree. What an interesting method. Foreshadowing is a literary device. Doing trees or tableau is another method for analyzing formula in propositional logic, which we'll probably see next week. Anyways, here are the exercises. I will do them throughout the week. If you are watching this and you want to go along, feel free to pause the stream or the VOD and screenshot, put them somewhere. It's going to be a lot of homework, huh? But it's fine. The point of this is learning logic is not passive learning. It is an exercise you must acclimate your mind to. It is a workout. It is hard work. The homework is necessary. It is part of the process. You need to form new connections in your brains by doing the work. Okay, so 1.6 to 1.11. And this is the last part, 1.11 to 1.14. Okay? People at home should be able to screenshot this and do the homework. I'll do the homework myself. I'll see you for the logic part next Saturday. For gaming streams, I'm gonna be streaming on Tuesday, 8 p.m. Mexico time. I'm gonna keep playing Cryptmaster. Thursday, 6 p.m. Mexico time, I'm gonna finish Esoteric Ebb. It's gonna be the last session. I can feel it. And then next Saturday, I'll see you with more logic. If you don't want to take a screenshot, if you want a copy of the book, here it is. It is Introduction to Mathematical Logic, 5th edition, by Elliot Mendelsohn. That is the exercise we're getting. As I said, I can... Whoops, we jumped to first order logic. Yeah. Okay, here we are. Okay, back to the homework. Okay, so yeah, no. What is the name of this book? Is the book with the riddles and the puzzles by Raymond Smullyan. The one with the more technical mathematics is Introduction to Mathematical Logic, 5th edition by Elliot Mendelsohn. Anyways, we should be nearing the 2-hour mark. Yep. We covered another unit. I think this is a good place to stop. I'll see you next week. Thanks, everyone. This was a great stream. Nice. Yeah, the one that had Knights and Eight puzzles, yeah, that is called... What is the name of this book? I'm sorry, I know it's a confusing name, but it's funny. It's funny. Anyways, good luck with the homework. See y'all. Bye-bye.